So the exams are graded via Gradescope, and we will release, after all of the students who need to take the exam have taken the exam, and there's still some who are not able to be there at the normal exam time, that will be taking it in the next couple of days. After their exams are taken and graded, then we will release your exams to you via Gradescope. So you will be able to see how we graded each problem, how we deducted each individual point, and you will be able to complain about this and issue a regrade request saying, I actually got this right, and you checked me wrong, and you're bad people. There's actually a bad people box in Gradescope that you can check. Anyway, so you will have an opportunity to do that. That day has not yet come. Yes?
Is our midterm grade factored into our semester grade?
Yes, your exam grade, for those of you who took the exam, your exam grade is factored in to your midterm grade. For those who did not take the exam because they were not able to be there and who are taking the alternative exam, they did not receive a midterm grade or should not have received a midterm grade. Okay. So if you feel like you are happy with your midterm grade, then probably you did well on the midterm exam. If you're not happy with your midterm grade, you probably did badly on the homeworks. It couldn't have been the exam. No, you know your homework scores. Any other questions about the exam? About logistics? Yes?
For the semester grade, was the distribution of grades just the same as the final?
No. So the median grade was higher than you would expect from the medium exam grade. So we shifted things using Professor Black's patented grading technology. We shifted the grades so they're somewhat higher. So there are a higher percentage of A's and B's than there would have been if we just went by directly from the raw scores. So it's not technically a curve. Basically what he does is he takes a big histogram he calculates scores, raw scores for everybody, takes a histogram, finds the first knee, and makes there a division between A's and B's, finds the next knee, and makes a division between B's and C's. And so there's a break. So this, in effect, means that people tend to cluster in A's and B's, and there tend to be fewer C's and D's. Any questions about that? So most people got an A or a B in their midterm grade. And the same procedure will be applied on the final grades. So note that if you're a grad student, in this class we do not give plus and minus grades, even though you're eligible to receive a plus and minus grade, because it's basically an undergraduate class that graduate students are allowed to take. And so it follows undergraduate grading policies. And we put everybody in together, and everybody gets just A's, B's, C's, and so on. Hopefully just A's, B's, and C's, right? So, yeah, that's just the policy in the course. Some people find it unfair. Complain to Alan anyway, because they would say, well, my B, is really at the high end of B. I should have got a B plus, and so my program would not be mad at me for getting a B. That it's for that reason. No. The plus minus thing. Okay, so today we're going to talk about lexical semantics. What is lexical semantics? What is lexical? If you say something is lexical, what do you mean about it? Referring to
lexemes.
Could be referring to lexemes, lexicons. What do lexemes and lexicons have in common? They're all about, yes, words. They're all about words. And lexical semantics is the semantics of words. Well, this begs the question, what is semantics? Semantics is about meaning, so lexical semantics must be about meanings of words. And that's what we're going to talk about today. We're going to talk about how you can characterize the meanings of words in systematic ways that can be useful for language technologies and NLP. So far, we've talked about a number of different topics. We've talked about information extraction, morphology, language modeling, classification, syntax and syntactic parsing. We've talked about all of those things. Now we're going to talk about something that matters. So we're going to talk about meaning. So all of these things that we talked about so far leave us trapped in the world of language. And semantics allows us to get outside of the world of language. Semantics is about the interface between language or signs and the real world. So this is what we're going to talk about moving forward. We're going to talk about semantics and also pragmatics. So they're sort of the glue that connects language to the real world. And in a sense, the other things that we've talked about are really only meaningful to the extent that they go through semantics. We have to take semantics for granted at some level or take it into account at some level in order for any of these things to make any difference. Otherwise, it's just sequences of characters. So we're going to talk about a few different approaches to semantics. We're going to start off this lecture by talking about lexical semantics. And we'll have also an introduction to distributional semantics as an approach to lexical semantics. Next time, Alan will talk to you about word embeddings, which are a clever way of getting at lexical semantics, and distributional semantics, vector semantics. Then we'll talk about model theoretic semantic representations for sentences. I'll do the first half of that, and Alan will do the second half. And we'll also talk about semantic parsing and semantic role labeling. So these are all semantic tasks that will allow us to connect these earlier stages in our pipeline to things we're actually concerned about. to things we actually care about. There are really three ways of looking at the meaning of words, which is, of course, what we're talking about today. One approach is decompositional. So you suppose that words have features. They have components of meaning. And you can break down a word into its meaningful components or decompose the word. It's also an ontological approach to meaning. This says, rather than breaking down words into their component meanings, this says we define the word in terms of its relationship to other words. So we have a big graph of word relations. And what a word means is what edges are connected to that node, where that word lies. And finally, there's a distributional approach to semantics. And this characterizes meaning in terms of the contexts in which a word is found relative to other words. So we're going to talk about all three of these, especially ontological and distributional approaches. So here's an example of decompositional semantics. So we have four words: boy, girl, man, and woman. This is suspect for a reason we'll talk about in just a minute. There's a problem here. Actually, there are a couple of problems, but there's one specifically. So in decompositional semantics, we might suppose that there are components of meaning. We'll call them features, which is what linguists would call them. And that boy is basically a vector of these features. It's like a multi-hot vector. So there's one dimension for human, one dimension for female, one dimension for adult. And the plus is like a 1, and the minus is like a 0. So it's 1, 0, 0. And girl differs from boy in just one feature. So girl is not adult and is human, but is female. So we break down boy and girl into their components, and these are the components that we're going to talk about. And you can, the idea is you can express man and woman in terms of the same features. In fact, you would suppose that every word could be expressed in terms of the same features, like a vector. Yes, Sophia?
No.
Oh, I thought you were going to make a comment. So what is good about this approach? Yes. Well, I said what is good about this approach. That would be what is bad about this approach, or what is the limitation of this approach. Yeah.
If you were trying to use that in your application, how does specific features make it easy to, I don't know, what is it something like you were trying to write something that was like, you need to know whether a word was feminine or masculine, and having it included and relatively easy to access, it might be nice for code.
So for some kinds of symbolic, so this agrees with certain types of symbolic feature structures that are used in certain kinds of grammar formalisms. So if you're making, like, there's one called HPSG or one called LFG, there are syntactic formalisms, but sometimes you have to make reference to to semantic features, and these are the same kind of representations that those formalisms would expect.
Those are just like some things that you really put on something.
Yeah,
And,
yeah, and grammars and lexicons. Um, so, so can you see any problems with this approach? Yes.
a lot of them. If they're all supposed to represent that same vector, isn't there going to be like these vectors are going to get really big, really quickly,
Uh-huh.
represent every word. And then also I would say the plus minus thing might be more of an issue because sometimes you might want to represent something as part of like a like there's some kind of category that belongs to that's not binary, so plus
Uh-huh.
or minuses might not be sufficient.
So what about this feature female?
Wouldn't it be nicer to have something called gender and have like
I have a multi-valued feature.
yeah, because not every word in like the English language is male or female.
Right.
Has like even has an opinion on female. Like other languages, maybe like is that chair female? Is it wrong to say it's not female because it's not female, or you know what I mean? Is not
Uh-huh.
female male, or is not female is not female?
Yeah. So the problem is you get like this. This is a complete rabbit hole. You have to decide. So who comes up with these features in the first place? Who defines the dimensions of the vector? So hopefully not me. I don't want to do that. So a human does this. And on what basis do they do this? Can they like do experiments to find what the features are? Well, maybe. But it would be very time consuming and take a lot of NSF money that NSF is not going to give you. So basically, somebody comes up with these things. They pull them out of a hat or out of something else. I don't know. And then they argue with one another about what the right features are. And there's not a good way of settling these kinds of issues. Any other problems that you see? What? Okay, out of vocabulary is a problem for this theory, this approach, and for the ontological approach. So how is out of vocabulary a problem?
Well, let's say a long time ago, we don't see it before.
Uh-huh.
And you wouldn't know whether it had a female or adult when all three came out.
Uh-huh.
So we have to do it.
So we either just have to guess or have to sort of leave it blank. Yeah.
So in this sort of system, is it still like decompositional semantics to say like if you have an out of vocabulary word, to like look at where it's used and like use that to decide what features it has, or is that
Well,
too close to distribution?
that would really be
Is that,
distributional
like,
semantics,
mixing those two, like, okay.
probably.
So you really
Yeah.
would just like if you see out of vocabulary with this kind of thing,
We're doomed.
you have no idea.
Doomed.
So many-
Yeah. Yeah, so of these approaches, in NLP, this is the one that's used least. But there are people who do kinds of decompositional semantics in NLP too. So this just reiterates some of what we've talked about. So where do the features come from? How you assign features to words in a principled fashion, which raises the out of vocabulary issue. How do you fill in the features for an out of vocabulary item in a principled way? How do you link the features to the real world? So this is, in a way, the least useful of these approaches. This brings us to ontological approaches to semantics. What is an ontology? Not an ontogeny, but an ontology. Yes. In a sense, at least classification systems are kinds of ontologies. So one specific kind of ontology that's a classification system is a taxonomy. What is a taxonomy? In biology, for example, but yeah, how does it work?
I don't know how to list them, but like there's a big overarching spectrum and there's families and genuses and species.
So it's a tree, right? Yeah. So taxonomy is an ontology with a tree structure. It's non-branching or non-looping, no cycles. It's just a tree. But an ontology doesn't have to be a taxonomy. It can be any set of relations between elements. So any kind of labeled graph where the labels are categories could be seen as a kind of ontology. Where the labels are relations, I should say. So this is an example from an ontology called WordNet, although WordNet people claim it is not an ontology, but they are wrong. So this here you have some nodes that are words and other words that are related to them by edges of different kinds. And the claim in an ontological approach to lexical semantics is that being woman, for example, the word woman's meaning is partly that it is a hyponym of human, and partly that it is an antonym of man, and that it has other kinds of relationships to other words in the lexicon. So that's what the claim of an ontological approach is. So we don't talk about inherently what the meanings of words are. We only talk about how they relate to other words. So in grammar school or in preparing for standardized tests, you may have learned the following terms: synonymy and antonymy. Who here is familiar with these terms? Hopefully everybody. Otherwise, you must have hired somebody else to take your standardized tests for you. So what is a synonym? A word with roughly equivalent meaning. And an antonym is a word with some kind of opposition in meaning. So these are only two relations that can exist between words. They're important, but they're only two relations. Some others that in some ways can be more important are hyponymy, hypernymy, meronymy, and holonymy. Holonymy. Holonymy, I'm not sure. I always confuse myself. I go and look it up. And then, holonymy sounds better in a way, but it also sounds like an operation. Like, I had a holonymy. Has anybody heard of these words before? You've heard of them? Not meronymy and holonomy. Yeah. What are hyponymy and hyperonymy? Right. Is that what you're going to say?
Yeah,
It's a subset superset relationship. Yeah. So a hyponym is has a subset relation with its hypernym. So this sort of summarizes these relationships. These are the ones you need to know about for the test. Right. So synonymy is equivalence, like small and little. Antonymy is opposition, like small and large. Hyponymy is a subset or an is-a relation. You'll sometimes hear it described in that way. So a dog is a mammal. Hyperonymy is a superset relationship. So a mammal has as a subset the dog. Mammals have as a subset dogs. Meronymy is a part of relation. So the liver is a part of the body. And the reverse of that is holonomy, a has a relation. So a body has a liver. Yeah. No, it's not possession. It's a part whole kind of relationship. Yeah, a teacher has a student would not be holonomy. A teacher has a face. Would be. We hope the teachers have faces. Yeah, it's a part whole relationship. It's not a possession relationship. Sometimes those get confused. In some languages, those are kind of separate, and in some languages, those are treated as the same thing, kind of, and so it gets confusing. But yeah. So any question about these? These are important things that you will see again. So now would be a good time to clarify. Yes.
So I'm trying to think of like, you had an example before, like, women's meeting, the meaning of the word woman is like kind of together in your head, it's like a synonym of, female or something. So, what would be an example of like, I tend to get hyponymy and, morality of confused.
Uh-huh.
Sort of like,
Lots of people do, and that's why we ask test questions or quiz questions.
So, could you give
But,
me like an example of something like of like a hyphenated or like narrative like what is the
So for women, it's a little bit hard because I can't think of a lot of words for kinds of women that are like not offensive. Right. So if you had female, then you could say that woman is a hyponym of female, and girl is also a hyponym of female. And girl and women are in some sense antonyms because there's an opposition between the two.
So what would you like?
And but because you can say that all girls are female, but you can't say like that, and you can say that liver is a meronym of woman. You say women have livers. But liver is not a hyponym of woman, because it is not the case that all livers are women.
I see.
So, so with hyponyms and hypernyms, it's a set theoretic notion. And we're viewing each of these things as a set and talking about this subset relationship between them. With meronym and holonym, you're talking about part-whole relationships. Good question. So this always confuses people. So this is a good time to get it straightened out in your head, because I guarantee you there will be a quiz question or an exam question that tests your ability to distinguish hyponyms from meronyms. So here is a little ontology. So we see here at the bottom that wall and surround as verbs, to wall, to surround, are roughly synonymous. So that this is a synonym, this is a synonym, and they have a relationship of synonymy between them. That's from WordNet. We'll get to that in a minute. But basically, what the two means is that's the second, so .v means verb, and .to means second sense. So it's the second verbal sense of surround in WordNet, this resource that we'll talk about. And this is the first verbal sense of wall. So these senses are synonyms. Build and destroy, this verb, are opposites of one another. So they're in a relationship with antonymy, and they're antonyms. Easy enough so far, right? So antonyms are tricky. Synonyms are tricky too. Synonyms are tricky because no two words have exactly the same connotations. You know, they're typically a little bit different. And so you have to ask yourself, well, how different can they be before they stop being synonyms and maybe start being even antonyms? And antonyms are tricky because in principle, any kind of opposition makes things antonyms. But any kind of minimal opposition. But there are all kinds of different oppositions that can exist. And this one between build and destroy, you know, is that building, this destruction is sort of the reverse of the operation that goes along with building. You know, but it's not the same really as the relationship between black and white. And you might ask yourself, well, if black and white are antonyms, are red and green antonyms? Or red and blue? So red and green are complementary colors, so they're sort of opposite. Red and blue are different colors. You know, so this is tricky actually. But here we have an enclosure and a fence. And the relationship between these is hypernymy, or an ISO relationship, with fence being a kind of enclosure. So fence is a hyponym of enclosure, a hypernym. And we can tell that this is a hyponym because all fences are enclosures. Well, what about door, wall, and building? How are they related? Yeah, there is only one left, but meronymy. Ever want to call someone a meron? You meron, you should get a holonomy. So, what is the relationship between door and wall? Door is a part of a wall. A wall is a part of a building. A door is a part of the building. So door is going to be a Door is a meronym of wall. Wall is a holonym of door. So holonym is easy to remember because holo sounds like whole. In fact, they're cognate. Um, they're cognate. So somewhere back in Indo-European history, they come from the same word. Um, so you've got a whole and a part. A holonym is the whole, a meronym is the part, and meronymy is the relationship between them. The same relationship going the other way is holonymy. So if you took as many, oh, yeah. Yeah, it would be. It's the arrows, the, um, yeah. Yeah, this should actually be hyponymy right here. Somebody else noticed this and I didn't get a chance to fix it yet. But yes, that's correct. Is there any what?
Like, if you know the word is like a kind of wall and wall is that automatically
Yes. So it's, these are both hypernymy and holonymy are transitive relations. So what would happen if you decided to get a bunch of dictionaries and pull out all of the words from those dictionaries and then put all of those words into a big ontology that everyone could use? What would that be called? Hubris, right? No, WordNet. So that's what WordNet is. So it's a big ontology. It's like if you took this in a way and applied it to a large English lexicon. It doesn't have every word in it because new words are constantly coming into being, but it has every word that was in the dictionaries that were available to the creators of WordNet in the 1980s and 90s. So in WordNet, words are described as having different senses. What do we mean when we say a word has a sense? Yes. Yeah. Uh-huh. Right. So foot could be a verb or it could be a noun. And foot as a noun could actually have different senses as well. Or there could be different noun senses. So there could be the foot that's at the end of your leg. Or it could be the foot of a table. The foot of the bed. So these would be different senses of that word. So in WordNet, then you take all of the words and you list their senses. And then the first thing that you do is you go and group together all of the senses of different words that are synonymous. And you call these sets synsets. Now, synset sounds a lot of fun, sounds like a lot of fun, but actually it's S-Y-N-S-E-T rather than S-I-N-S-E-T. So you shouldn't get any ideas. They're synonym sets. And then, so you take and group everything together into these synonym sets, and then you associate these synonym sets with one another via relationships like antonymy hyponymy, and meronymy. So the main relations, so they're the synset relations, and then between these synsets, the other relations exist. So in essence, what WordNet is a glorified electronic thesaurus. What is a thesaurus? A thesaurus is that book that you consult when you're writing a paper and you want to sound smart. And so you try to look up a more educated or fancier sounding word for the simple words that you're trying to say. And so your professors will read your paper and think, this student used a thesaurus to write this.
It's a website now.
Yeah, it's a website. I'm very old. In my day, people read these books on paper, um, but yes, Google. What is this Google? I I used Google when it was still on the like in the dorm room of Page and Bryn. Anyway, I'm that old, and I was already in college, so. So here are some examples of synsets. This is a synset for dog. This is full of awful language, but as a lexicographer, you can't make judgments. Um, you just have to say what is out there. So a dog is, the first sense is canis familiaris, um, like a puppy dog. Um, a frump, a dull, unattractive, or unpleasant girl or woman. An informal term for a man. Notice this is totally unfair because the first sense for women is like something negative, but the first sense for man is just informal. And the example is you lucky dog. But then if you go down one, they do have a tad down to a blackbird dog town heel, someone who is morally reprehensible. A hot dog, hinge catch that fits into a notch of a ratchet to move a wheel forward. Never heard this called a dog before, but apparently it's called a cow. Yeah. They're, I think, ranked. They're supposed to be ranked by frequency in some sense. So the most frequent um, sense is number one. Well, and their limited corpus. Anyway. But this is basically how synsets work. So you're grouping together dog, domestic dog, and canis familiaris as a synset, and then you're looking for relationships between this synset and other synsets. So we talked about how hyponymy is sort of is a transitive relation. So you can get taxonomies by looking at the hierarchy of hyponyms within WordNet. And this is an example. This is the one for fish. So you start at the bottom. It's a fish. That's a hyponym of aquatic vertebrate. This is a hyponym of vertebrate. This is a hyponym of chordate. This is a hyponym of animal. This is a hyponym of organism. This is a hyponym of animate thing. I don't know where the WordNet people came up with these things from. Which is a hyponym of whole or unit. Which is a hyponym of object. Which is a hyponym of entity. So in a way, this is sort of like a biological taxonomy. But it differs in some respects too, in that it respects more what the words mean rather than what the biologically correct family tree of them is. And obviously not everything falls into a biological taxonomy. One interesting thing you can do with this is you can calculate the information content of words. So you might think all words have the same information content. But this is actually not true. So entity is a very abstract word, whereas hill and coast are rather concrete words. Meaning that hill and coast really have more meaning. They have greater informational content than entity does. And by taking the negative log of the number of words that are equivalent to or hyponyms of a word, C, over the number of words in a corpus, you can calculate the information content of a word. And so that's what's given beside these words. You can use WordNet. In fact, many of you will use WordNet. Why will you use WordNet, you ask? You'll use WordNet for your projects. And why will you use WordNet for your projects? Did you have an answer? Because you are evil. Because you want your questions to be more difficult to answer. So you're going to do something like take words with high information content from your questions, and you're going to substitute them with synonyms. Or you're going to take words, you're going to do antonym substitutions of various kinds and switch around the value of yes/no questions. You're going to do things like that. And why are you going to do things like that? Because you're bad people. Bad people who want to make life more difficult for your competitors. So you can use, there's an NLTK interface that works just like this. You can look into that at this link here. There are other interfaces to WordNet for other languages that are available there as well. So WordNet is useful. Lots of people use it for lots of things. But there are limitations to this kind of resource. So one is that it requires many years of skilled manual effort to create such a resource. So this is why they're not WordNets for every language. They're WordNets for some languages. So there's English WordNet, obviously. There's German WordNet. There's Japanese WordNet, two Chinese WordNets. There's like competing Taiwan and mainland China WordNets. And there's a Korean WordNet. There are WordNets for a few languages, but this takes a lot of work. And most of them are not as extensive as the English WordNet. In a lot of cases, also, the lexicographers were not as skilled as they should have been. And this has led to inconsistencies. And because an ontology is only as good as the ontologist, this is a problem. This is not data-driven. This is driven by a priori decisions on the part of lexicographers. So wouldn't it be great if we could have a data-driven approach to lexical semantics? Wouldn't it be great if we could learn relationships between words directly from data, even with no supervision? Well, buckle your seatbelts, because now we're going to enter the exciting world of distributional semantics, of beef. We're going to enter the exciting world of beef. So here you see, this is from a corpus called the Brown corpus, and made with the concordancing software, where it just lists off all of the occurrences of the word beef, sorted by the following word. What do you notice about beef? What could you learn about beef from these words? If you'd never heard the word beef before, you knew English, but there's this new word. Let's say it was schmog. You see a new word, schmog. What can you learn about schmog from these contexts? Yes.
Looks like it's like beef.
Why do you say that?
It says just dash in the program, so that makes it seem like beef and that.
Uh-huh.
Also, just like other types of food.
So there are a lot of food words around, things that you might eat. Yeah. So this definitely has something to do with food from just the domain that you get from surrounding words. What else? What else do you learn from it? It's related to cows. How do you know that? Beef, cattle, beef, cattle, beef, cattle, beef, cattle, beef, cattle, beef, cattle, beef, dairy, beef, dairy. So how do you know what words mean? How did you learn the meaning of beef? Or the meaning of the word tofu? Is that what happened? They said tofu. Tofu.
Well, like the basic word we learned just by listening to the like in the middle, kind of talks about it a lot, and we're around it, and you just sort of develop these like figure out.
But how do you figure that out? You have to have some basis for doing that. How do you figure it out?
Same way I train my dog to sit, like I say sit, and so for me, after we're sitting and you say sit must be those two words. I don't think she knows what the word sit means, but I think she has an association with it. So I think that humans must be sort of the same thing. And that if we see something or it's reference to something like that, say that word and know it must be the same thing.
Neurobehaviors. Well,
I know I am. And it's
what about the meaning of the word dream? Do you have a dream? How do you know what that means? Did somebody see you dreaming and say, look, that's a dream? You know what words mean because of the context in which you hear them. And that context has two types. One type is where it occurs relative to other words, and one type is where it occurs in the context of other sensory experience. So if we are doing NLP, we don't have access necessarily to other sensory experience, unless we're doing multimodal stuff, in which case talk to LP Morency and Alex Hoffman. But we do have access to the place words occur in context. And you could learn a lot about what beef meant just by the context in which beef occurs. Same thing with chicken. You can see a lot about how beef and chicken are both the same and different by looking at the context in which they occur, even in a relatively small corpus. What you can do, this goes back, One of my heroes is a guy named Zelig Harris. Zelig Harris was a linguist in the early 20th century, first half of the 20th century. Actually, he lived into the 1980s, but he did most of his work in the 1940s and 50s. And Zelig Harris was interested in studying the indigenous languages of North America. And he wanted to put this study on a scientific footing. He wanted to make sure that they could study those languages and document them in ways that were independent of the grammatical traditions of Europe and that were based on science. And so he developed a set of procedures building on earlier work where you could take a corpus of data from a language that you didn't know anything about, and you could apply these procedures, and you could discover the structure in the language. You could discover how many phonemes it had, which are units of sound. You could discover what the morphemes were and how they were combined. You could discover what the constituents were and how they went together. And most radically, he said you could discover the meanings of words because they're distributional structure. That you can know, the reason that we know, his example is terrible actually, but he said the reason that we know that eye doctor and oculist. So I only know this word from Zelig Harris because it means an eye doctor. Apparently it's a word that was used in common use in the United States in the 1950s. So we know that an eye doctor and an oculist are the same thing or have the same meaning because they have almost an identical distribution. They occur in almost the same kinds of contexts. They're similar. But if you look back at these, they actually occur in different contexts. Similar domain, but beef never occurs before coop, for instance. There are no beef coops. And chicken never occurs before cattle. There are no chicken cattle. So they wouldn't be the same, but they would be somewhat similar. And the idea was that things that are antonyms or synonyms are going to be more similar in their distribution than just two words chosen at random. What? Yeah, antonyms are going to be very similar in their distribution. Because if you think about it, antonyms is a kind of similarity. We think opposite, that means totally different. But actually, things that are antonyms are mostly the same, they just differ in one thing. So you can following this idea that Zelig Harris had, you can take words that occur in a corpus and look at what other words they co-occur with. So you take a window, a few words wide, and you move it across the corpus. You have a little marker for the word in the center, and then space for the words on either side. And every time that word in the center co-occurs with another word in this window, then you mark it in your table. And so you end up with vectors like this. So for apricot, it co-occurs with, in this toy example, with boil, lard, sugar, and water, once each. Pineapple occurs with boil, lard, sugar, and water, once each. Digital occurs with data, function, lard, summarize, and so on. So all of these occur with lard. But you see that apricot and pineapple have vectors that are more similar to one another than digital and information. Yes?
So by that level, if it's quite
Uh-huh.
not only apricot and pineapple similar, they use them actually by that level.
No, by that logic, they are more similar to one another than either is to digital or information. But they're they're rather close synonyms. So the idea ultimately, I mean, yes, if you look at Zelikaris's original example, then it seems that way. But what we're really saying is that there are degrees of similarity. This is a real valued thing. And you can compare the similarity between pairs. But it's not an absolute thing. So these are co-occurrence vectors. And you can compute the similarity between vectors, and it correlates with the similarity between words in terms of their meanings. So here's a problem. Some words occur together a lot just because they're common words, like of and the. Do you think of and the share anything in common in meaning? But of the occur, they're both some of the most common words in English, so they occur together lots and lots. So what are we going to do about this? If we just use raw counts, like here, if we just use raw counts, we're going to think that of and the are similar to one another, or highly similar to one another. Well, are they? Yeah, they're I guess similar in the sense that they have low information content. But for tasks like this, they're going to be similar to everything. Because any word is going to co-occur quite often with the and with of. How would we characterize the similarity, by the way? How would we compute the similarity between two vectors? This is something we'll talk about more next time. But yeah. So we take the cosine similarity. Why the cosine similarity? Why not the dot product? Uh-huh. Right. So we don't want to care too much about what is in each of these, what this value is. Specifically, we don't care whether the vectors are long or short. What we care about is the relative angle of the vector. And so this is best measured with cosine similarity. So we've solved the similarity part, but what do we do about this? About the fact that words that are very common are going to co-occur just by virtue of being very common and not by virtue of being similar in the ways that we want to capture. Well, a solution to this, and we'll go into more detail next time, is point-wise mutual information. This is a very simple concept. It's a measure basically of the degree of collocation between two words, the two events. So if you have two words, W and F, then pointwise mutual information is the negative log of the probability of W and F occurring together, in the same window for our purposes, and the product over the product of the probability of W occurring and the probability of F occurring. It's very simple. I hope I didn't say negative log. I'm sorry. I was talking about negative log of something else earlier today, and it seems to have stuck. The log. So what is this? What does this do? So two words. Let's say the two words are Jack and rabbit. And we compare these with the rabbit. So what is our pointwise mutual information going to look like for these two examples? So let's say rabbit is not super common, but the is very common. And Jack is also not very common. But and the rabbit occurs a lot together, and Jack rabbit also occurs quite a bit together. What is the PMI of these two examples going to look like? Yes.
Jack doesn't have a higher premium because Jack itself has a lower power than
Right. Exactly. So this is Jack and this is rabbit. In this probability of Jack is going to be quite low. And the probability of rabbit is not super high, but it is somewhat higher. When we contrast this with the probability of the and the probability of rabbit, the is super common, rabbit is also not. It's not that common, but the denominator is going to be much smaller for jackrabbit than for the rabbit. But the numerator for the rabbit, the numerator is going to be probably larger for the rabbit than for jackrabbit, but this is going to be, the denominator is going to more than make up for this. Does this make sense? Jackrabbit would have a higher PMI. What you can do is you can take your word vectors and you can weight them via pointwise mutual information. Or better yet, as we'll talk about next time, you can weight them by positive pointwise mutual information, which is just applying a floor of 0 to pointwise mutual information. Well, the interesting thing about this is that it works. That is, you arrive at rather meaningful results when you apply this. And in fact, this basic idea is the foundation of much of language technologies and NLP today. So whenever you hear people talking about word embeddings or skipgram or continuous bag of words, or even about BERT, at some level, they're talking about this idea of distributional semantics. So this actually works. And here's a rather simple example that's done just with these word co-occurrence vectors like we were talking about here, weighted with pointwise mutual information. So you have these words, rum, right, ancient, and mathematics. and then you list the words that have the highest cosine similarities, over this in this corpus to those words. So for rum, you have vodka, cognac, brandy, whiskey, liquor, detergent. Somebody was like taking the Tide Pod challenge back in 1998. Cola, gin, lemonade, cocoa, chocolate, scotch. I'm not sure what Noodle was doing there. Tequila, juice. What about write? Well, read is the number one thing. Speak, present, receive, call, and so on. For ancient, you have old, modern, traditional, medieval, historic. You think it's not working? This is completely unsupervised. This is magical. Of course they go together. They're antonyms. Now, what I have a question about is Indian. Why does Indian go with ancient? Or African or Japanese? They're adjectives. Well, they do have ancient civilizations, but why, what? Yeah, yeah. So what about mathematics? We've got physics, biology, geology, sociology, psychology, anthropology, astronomy, arithmetic, geography, theology, economics, chemistry, scripture, biotechnology. So you might ask, why are theology and scripture in the same list with mathematics? Why is that? Yeah, because like mathematics, they all bring you closer to God. What? So actually, they do work, and they actually work better now. This is from 1998, and we've got even better things now, trained on larger corpora, and you can get like spectacularly freaky kinds of results out of these sorts of models. Um, so this is not to say that decompositional models of semantics or ontological models of semantics don't have their place and are not useful and valuable for certain things. But distributional models of semantics are more what you will encounter in most NLP tests. And that's why we're devoting a whole lecture next time to this topic. Any questions about this leading up to tomorrow? Because Thursday. For me, tomorrow means the next day, and yesterday means the previous day that I'm going to see you. Anyway, so I do that. So next time will be, in a way, one of the most important lectures of the year, so of the semester. So I suggest that you be here and listening and ready with some good questions. But do you have any questions now? Okay, let's go.